All right, IB Physics. I know that a lot of you guys have decided to do higher level engineering, and the first unit in higher level engineering is rotational motion. This video is going to be made in a bit of a rush, so I apologize in advance if I'm going to be making a lot of mistakes in language or I have to erase stuff and start over again. I'm doing this about half an hour before our class today, so it could be a bit interesting. All right. For rotational motion, the reason we didn't cover it in mechanics is because things get a little bit wacky, okay? If I take a look at this video on the left of a guy dropping two different objects down a ramp, those objects look pretty similar. In mechanics, we treated those objects as point masses and didn't have to worry about energy being dissipated in the form of rotation or anything like that. So those point masses should have the exact same acceleration and they should be sliding down at the exact same rate. And that rate would be the acceleration of gravity times sine theta, the angle, this angle over here of the ramp. So g sine theta would have been the acceleration of those objects if they were point masses. But in this case, you see that one object is accelerating faster than the other, which obviously tells us that when things are rotating, things are a little bit different. Now, on the outside, they look like they're the same, but definitely on the inside of those boxes, one is full of something and the other one's empty. So which one would roll down faster is something that we're going to be able to answer by the end of this unit. Okay, so just to go back here, rotational mechanics doesn't treat objects as point masses. Okay, that's the difference. And we have to account the fact that for rotation, there's other forces and other terms involved that make things go different. So rotational mechanics deals with quantities such as angular velocity, angular acceleration, torque, and inertial mass. These are the key terms that you have to be able to develop definitions for to be able to explain what's happening in this setup over here, okay? And rotational mechanics explains why the pulley systems we used in chapter 2 and rolling objects. Remember we did a lab where we rolled a ball down a ramp and we tried to calculate G and it didn't actually give us G, it gave us something less? Well, in all those labs, we said that that was due to friction, but that's not true, okay? And I didn't tell you guys that. It's because some of the energy is being dissipated in the form of rotational motion, okay? And that's something we're going to be able to answer by the end of this unit. Okay, so the first thing that we got to do when we're talking about rotational motion is to review something that we've already done in simple harmonic motion and circular motion and talk about angular quantities, okay? It's much easier for me to look at an object that's rotating and talk about it in terms of how many revolutions per second it's making or how many radians per second it's making. So we have different ways of describing the motion of a circular object. If I try to describe the linear motion, like for example, this point on that object moving, it's going to be a blur. It's going to be really, really hard to see and it's going to be hard to measure. But I would be able to attach a sensor here and calculate how many times this wheel rotates, which is a lot slower and a lot easier to measure. So when we're talking with rotational objects, we often use terms like angular quantities, okay? Stuff like angular frequency, which we're going to talk about right now, okay? So things that we've already seen in the past when we talk about angular quantities is this unit, which is angular frequency, 2 pi over the period. If I measure the period of that wheel, the time it takes to make one full complete cycle, 2 pi over the period will give me a unit called radians per second. Okay, that's how many radians per second that object is rotating, and that's an important unit to remember. So angular frequency or radians per second. Okay, we can call that also angular velocity. So angular velocity, okay? So that's a term that we played around with before, okay? So if this hand, for example, pulls that wheel and makes it rotate, it's going to be applying a force, and that force is called torque, which we're going to learn about later on. And that force causes this tire to experience a form of acceleration called angular acceleration. It's going to go from 0 radians per second to a certain amount of radians per second. You're going to see that a lot when you're reading this, the beginning of this unit, okay? So I just wanted to make sure that we all are familiar with angular frequency, okay? And then that other term, this term here, alpha is angular acceleration. Oops. Okay, and that's just the rate in change. So it's the rate in change in my angular frequency over time is going to be equal to my angular acceleration. So if an object is at rest, its angular acceleration is 0. And then if I apply a torque, which that hand is doing, the torque is pulling on that tire, it's going to make it start to rotate at a different speed, I have now, that torque is going to be creating an acceleration. Remember, force is equal to mass times acceleration. Well, this torque is going to be creating an angular acceleration, and that angular acceleration is going to cause a change in my angular velocity. Okay, so you'll see that as we move along, it's going to be pretty easy for us to learn this section, because it's just like the kinematics that we did in chapter 2 when we talked about linear velocities and linear motion, except now we're applying the same formulas to look at changes in angular motion. Okay, so how do I convert angular speed into linear speed, or vice versa? How would I convert linear speed into angular speed? Let's go back and just kind of remind ourselves of some geometry that you have learned in mathematics. Okay, so if I have a circle, okay, and that circle has, yeah, I got you. All right, that circle has a radius of r. Okay, and let's say I'm at point A, and that wheel starts rotating to point A prime. Okay, that point has moved from here to here in a certain amount of time. Okay, I'd be able to calculate the velocity by looking at the distance or the displacement. I can look at the velocity and look at the displacement over time. Okay, so that would be that arc. That arc would be my displacement, which let's call that S. Okay, so that arc is going to be my displacement. Okay, and that would be the angle at which I've moved from going from point A to point A prime. Okay, and if you remember, we always applied this formula for arc length and radius. S is equal to theta r. So my displacement divided by r is going to give me my angle in radians. Okay, if you recall from our previous units. Okay, so my linear velocity, my change in distance over time, which is that arc length S, that arc length that I moved S over time, is going to give me my velocity. All right, and then I'll be able to then calculate my velocity. But how do I go from my velocity to my angular frequency? So velocity divided by radius is equal to angular frequency. Why is that? If I take S divided by R over here, S divided by R is theta, okay? S divided by T divided by R is going to be equal to velocity divided by R, which is my angular velocity. So if you take any measurement, such as the arc length divided by R, that's going to give me theta. If I take my velocity divided by R, that's going to give me my angular velocity. Okay, and vice versa. I can convert angular velocity times R is going to give me my linear velocity. Okay, these are important terms that I'm going to highlight here that we need to be able to play around with. Okay, so then if I look at my change in angular velocity over time, that's going to give me my angular acceleration. Another thing I can do, if I knew my linear acceleration, okay, and I divide that by r, it's also going to give me my angular acceleration. So what this is saying is that if you just take your linear terms from the kinematics, like velocity, displacement, acceleration, and if you divide it by the radius of that rotating object, you will get the angular terms, such as angular acceleration, angular velocity, theta, okay? And just remember, you can convert them back to the linear term by multiplying by the radius. So I can convert my angular acceleration back to linear acceleration by multiplying by the radius. Okay, so that's how we convert linear quantities into angular quantities, just by playing around with the linear terms and dividing by the radius will give me my angular terms. Okay, so what can we do with these angular terms? Well, first, before doing that, I just wanted to point out that you can physically convert all the linear kinematics equations into the angular kinematics equations. All right, so just by saying what I said. So if I had my linear acceleration divided by the radius will give me my angular acceleration. And you see these formulas look almost exactly the same, or they are the same. Okay, so for example here, my final angular velocity is going to be equal to my initial angular velocity times my angular acceleration times time, which is the same as this one. My final linear velocity is equal to my initial linear velocity plus AT. We played around with these formulas for 2 years prior to this with Suvat equations. So the same Suvat equations can be applied to angular velocities and angular accelerations, and in this case, that would be angular displacement, my angular displacement. How many radians have I moved over a certain amount of time? That's a pretty cool relationship, okay? All right, so let's go through some example problems. All right, what is the linear speed and angular speed of a child seated 1.2 meters from the center of a steady rotating merry-go-round that makes one complete revolution in 4 seconds, okay? So the linear speed and angular speed of a child seated 1.2 meters. So I should write down these terms. The radius in this case is going to be 1.2 meters. All right. And the question is asking me for my angular velocity and my velocity. We don't know what those are yet. Okay. But I also know that the period, sorry, I'm getting used to this pencil. It keeps on switching. The period is equal to 4.0 seconds. Okay, so how can I get it? So there's lots of ways I can do it, and I can cheat. I can really cheat and make this pretty simple, because one full circumference is going to be 2 pi r. Okay, so I can find the total displacement that the child makes over the whole circle, and then divide that by the period. That's cheating. I don't have to know any formulas for that. So I don't really want to do that. I want to use my knowledge of angular speeds to do this. So remember, angular speed is equal to 2 pi divided by the period, which is going to be 2 pi divided by 4.0 seconds. Okay, that should give me the answer. Unfortunately, I don't have my calculator with me. I don't have time to calculate that, but that's how I would calculate my angular velocity. And if I want to get the linear velocity from that, remember, my linear velocity is going to be equal to my angular velocity times the radius, which is going to be whatever was here multiplied by 1.2 meters. So 6.28 divided by 4, that's roughly around 1.5. So 1.5 times 1.2 is going to give me my linear velocity, which would be over here. Sorry, guys. I ran out of time to make this, to do the calculations, but I'm just going to show you the method about how to do it. Okay, so, oh yes, our wonderful physics fails videos. And you can see this guy. This guy's breaking his back with centripetal force. What a guy. Risking it all for physics. All right. So calculate the angular acceleration of the merry-go-round if a motorcycle causes it to move from 0.5 rotations per second to 10 rotations per second in a time span of 3 seconds. So the question's asking us for the angular acceleration. Okay, so angular acceleration is equal to my change in angular velocity over time. Okay, so how can I figure that out? So you got 0.5 rotations per second and 10 rotations per second. How do I convert something's in the units of rotations per second, okay, into an angle? So 0.5 rotations is going to be pi radians per second. Okay, so it's going from my initial is equal to pi radians per second, and my final angular velocity is going to be 10 rotations per second, which is going to be 20 pi, all right? Because each rotation is 2 pi radians, so 10 times 2 pi is going to be 20 pi radians per second. Okay, so those are those terms. So my angular acceleration is going to be 20 pi minus pi divided by 3 seconds. That's 19 pi divided by 3 seconds. That's going to be my angular acceleration in radians per second squared. Okay. Oh, that was pretty simple. Okay. Now, what does that mean for this guy? Assuming that the radius of the merry-go-round is 1.2 meters, calculate the total linear distance that a kid moves around the merry-go-round while accelerating for 3 seconds. So this is what I was talking about, how you have to apply those kinematics formulas. Okay, so we have our angular acceleration, 19 pi over 3. Okay, and then what else do I have? You have his initial velocity. You have his yeah, I don't have the final velocity because this is a different time frame. So assuming the radius of the merry-go-round is 1.2 meters, calculate the total linear distance that a kid moves around the merry-go-round while accelerating for 3 seconds. Okay, so just like in kinematics, we have our Suvat formulas where S is equal to ut plus 1/2 at squared. Okay, if I want to find S. Okay, well, in order to find S, I can find the total angular displacement the kid went multiplied by the radius is going to give me S. That's the logic. Okay, so what I need to find is the total angular displacement. Okay, so if I go back to this formula list over here, I can use this one right up here. I can find the angular displacement. I have the angular acceleration that I calculated. I have the time, which is 3 seconds. I have my initial angular velocity, and let's just say that I'm starting at 0.0 in that case, so let that term be 0. Okay, so now I can calculate theta if I go back to that. So let's go apply that equation. Okay, so my theta is going to be equal to times time plus 1/2 t squared. Okay, and in that case, theta is going to be equal to pi times 3 plus 1/2 19 pi times 3 seconds squared. Okay, and once I solve that out, that gives me the total theta that I've moved. The theta that I moved times 1.2 meters is going to give me my total displacement. And that's the logic behind solving that. Okay, so what that would mean is how many meters did that kid go wow, 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 wow. He probably didn't go that far. He probably went wow, right? And that's a projectile motion problem, which would be a different problem to look at. But yeah, that would tell us in 3 seconds, how many revolutions and how many meters did that kid fly? How much blood rushed to the top of his head? At which point did he pass out? That would be an interesting question as well. Okay, so here's something that's more realistic, IB related, none of those prank problems. Okay, here, this is an ancient hard disk. You guys probably have solid state disks now, but this is an ancient hard disk, and information is written like a CD in grooves and lines. Okay, but the rate that information is read should be constant. So as my reader moves up and down, the CD or this disk has to change its velocity. That's that sound you would hear when your hard disk is working. It would change its RPMs so that this reader is going to read information at the same rate. Okay, so if my reader is reading over here and it needs to read at a rate, maybe what's going to happen is this disk is going to speed up. If it's out here, the velocity out here is going to be larger than the velocity over here for the reason that theta, or sorry, not theta, your angular speed times r is going to be equal to velocity. So as I increase my radius, okay, my velocity out here is going to be much greater than the velocity over here. So point A's velocity is going to be greater than point B's velocity if that object has the same RPM. So the disk has to change its rotation in order to be able to read information at the same rate. Okay, that's that sound that you would have heard before. Okay, so an old computer hard disk rotates at a frequency of 3,000 hertz. Assuming the disk doesn't adjust its frequency, calculate the linear reading speed at a distance of 3 centimeter radius. Okay, so in order to calculate the linear reading speed, the linear reading speed is the velocity, which is equal to my angular speed times r. Okay, how do I get my angular speed? Well, angular speed is equal to 2 pi over the period, which is equal to 2 pi times the frequency. I gave you the frequency at 3,000 hertz. So my angular speed, which is 2 pi times 3,000 hertz times 0.03 meters is going to give me my speed. Okay, that's pretty simple. And at a 6 meter radius, I would do the same thing. 2 pi times 3,000 hertz times 0.06 meters is equal to my linear speed. Okay, so in a nutshell, all right, where we're going with this, in today's class, we just walked through how to use the SUVAT of rotational motion. And you guys, and I even introduced a unit called RPM, and you got to convert RPM into this, which is angular speed, which is radians. Okay, so you got to be able to do that. I put on our doc and on Quia a few simple problems to convert linear motion into rotational motion to get that practice, because it's important to be able to be comfortable with these terms. But where we're going is looking at just Newton's laws. Torque is a force that causes an object to change its rotation or change its angular motion. Okay, and something that we look at, F equals ma would have been for linear motion. When we talk about rotational motion, torque, which is the force, is equal to mass times acceleration, but mass is based on the inertial mass, which is based on this term over here, we're going to talk about next class. And then we can treat all rotational motions with conservation of energy and collisions with momentum. All right, and all this stuff is what we're going to go through by the end of this week. All right, so you can start getting ahead of me and reading that section. All right, and just to summarize though, this table here, we need to be pretty comfortable doing that, and that's what the problems are there for. All right, good luck.